Let's take a look at section 7.4, continuation of the conversation we've already been having, and that is let's take a look at section 7.4, and that is a deeper look at proportional relationships. So proportional relationships are really a continuation of the conversation we've already been having, and that is using ratios and fractions to show the relationship between two variables or two quantities. So proportional relationships are where the ratio between two quantities does not change with time, and there are a couple of other characteristics that are required for a relationship to be proportional. So first of all, let's take a look at how we would use proportional relationships and describe them in multiple representations as an equation and also later on as a graph. So remember, if we just go back to the first three sections of the chapter, we have looked at representing relationships and problems with diagrams, with tables, with double number lines, and with strip diagrams. So let's take a quick look. So activity 7i, if, for example, we have two strips, strip 1 and 2, and they're stretchy, they're elastic. But when you stretch one, you stretch the other one just as much, and their lengths stay in a 3:5 ratio proportion. So, for example, if we started with strip 2 being 5 centimeters, then strip 1 would be 3 centimeters. But if you stretch both of them by a certain amount, then strip 2 is going to be 7.5 or so, and strip 3 is going to be 4 and a little bit. But still, do you notice that the strip 2 is going to be 5 of those rectangles, and strip 1 is going to be 3. So they're getting stretched, but their proportional lengths remain the same in a 3:5 ratio. So how many of strip 1 does it take to make strip 2? We kind of looked at that before in a slightly different example. So for example, if we have strip 2, and this is strip 1, okay, so we have a 5:3 ratio, right? Now, how many of strip 1s does it take to make strip 2s? Do you think that's going to be more than 1 or less than 1? In fact, strip 2 is longer, so we will need more than 1, right? So how many? Let's say if one strip 1 is that much, then each one of these rectangles is a third of strip 1. And how many of those rectangles do we have in strip 2? That's 5/3. So you will need 5/3 or 1 2/3 of strip 1 to make strip 2. Well, what happens if we are looking the other way? Now, how many strip 2s does it take to make strip 1? Is that going to be greater than 1 or less than 1? It's going to be less than 1. Notice we're switching the whole here. So now we have one strip 2. So if we have one strip 2, then each of these is going to be a 5th. Right? Because there are 5 of them to fill the hole, to fill the one. So each of these, all the rectangles are a 5th. So we would need 3/5 of strip 2 to make strip 1. In fact, we didn't even look at the centimeters. Right? We could have completely ignored all of this, and all we needed to know was that these rectangles were the same, and one of the strips had 5 of them and the other strip had 3. So in fact, this was unrelated to any of the actual measures. It was just the relative measures of strip 1 and strip 2. So given a value for x, how can you find the corresponding value for y? Now x is our length of strip 1, and y is our length of strip 2. Okay, so y would equal how many strip 1s? Well, y is going to be 5/3 of strip 1s. Well, what if you are given y and you want to find x? How many y's, how many strip 2s do we need to make strip 1? It should be less than 1, right? So 3/5. So 3/5. So the first equation here says that to get y, we need to take 5/3 of x, right? And that 5/3 is greater than 1, so this is going to be greater than x. And the second equation here says if we want x, we want to take 3/5 of y. So write and explain as many equations as you can that relate x and y. Also write incorrect equations that you think students might write to relate x and y. And I'm going to let you finish this before you move on to the next section. Now, in activity 7J, what if we now have, instead of the situation here where we were measuring in the same dimension, right? All of the lengths went from left to right horizontally. What if now we actually have 2 dimensions? So now instead of having a double number line that are parallel, we now have 2 number lines that are perpendicular to each other. So because we're measuring the horizontal length of the ramp and the height of the ramp. So let's see, suppose a ramp is 4 feet long and 3 feet high. Imagine other ramps that are x feet long and y feet high, but those lengths and heights are in the same ratio. So x and y vary together in a proportional relationship. How many groups of their lengths amounts, x feet, does it take to make the height amount? So how many groups of the lengths takes to make the height? So if we started off with 4 feet by 3 feet high, 4 feet long by 3 feet high. If we're going to be using x as our length, so 1x, then how many x's do we need to make a y? So this would be a quarter and a quarter and a quarter and a quarter. And here, they're all the same length, so these would be a quarter of x. So how many quarters of x do we need to express y? How many quarters? 3/4 of x. How many groups of the height does it take to make the length? Okay, well, let's take a look at looking at it the other way. So if I want to look at y being 1, so then all of these rectangles are a third. So then we need 4/3 of y to make x. Does it make sense that to get y, we multiply x by something less than 1? And to make x, we need to multiply y by something more than 1. Do the answers depend on the specific number of feet in lengths and heights? We didn't even look at how long everything was. We were just looking at the fact that these rectangles were the same length. Okay, and they were relating one length to the other. So it does not depend at all on the specific number of feet in lengths and heights. What it depends on is the ratio. So whether we're looking at a small ramp, this and this would be equations to describe it, or an overall large ramp, as long as the ratios of the 2 variables are the same, stays constant, those equations will be the same. So write and explain as many equations as you can that relate x and y for these ramps. Well, I could say that if I took 4 y's, that would be the same as 3 x's, right? Or, and there are lots of others. We could do 4y minus 3x would equal to 0. Describe in as many ways as you can what is the same for all the ramps. Okay, so I'd like you to take a minute to do that, and then we'll come back and discuss it. So what were some of the things that you noticed that were the same? Well, we can say x is on horizontal, y is on vertical, right? There's a 3:4 ratio. Now, the other thing that you may have noticed here is that the slope or the steepness of the ramp is actually the same. You can kind of see the smaller ramp in here, right? And it overlaps perfectly. So the steepness of the ramps are the same. And also, where do the ramps start? Right? Do you see that they're all tucked into the 0, 0? So when we have no height of the ramp, there will be no length, no width. No height, no width. So they go through 0, 0. So now pick another fixed ratio and make sketches of ramps and write and explain equations to relate the lengths and heights of the ramps in that ratio. And I'm going to leave this up to you to finish. When you do that, you can take a look back at these things that were the same now and see which ones stay the same after you've picked another fixed ratio. And I think what you'll notice is going to be very interesting. I think what you'll notice is that x is on the horizontal, y is on the vertical is going to be the same, and they're going to go through 0, 0. So this going to go through 0, 0 is a very important aspect of proportional reasoning, that when one of the quantities is 0, then the other one has to be 0. And we'll get back to that soon. So now let's take a look at graphs and equations. Why do lines have a specific type of equation? During this activity, pretend that you don't yet know how to formulate equations of lines. Consider the line that goes through the origin 0, 0, just like our ramps did, and the point 2, 3 for all the points x, y on this line. X and y are in the ratio 2 to 3. Okay. So if you're looking at this ramp, this line, it goes from 2, 3, right? So we have our x units and our y units. And this point, whatever this point x, y is, it also is in a ratio of 2 to 3, where both of the axes were stretched a little bit. So explain why for all points x and y on the line for non-negative values of x and y only, x and y are related by the equation. Y equals 3/2 x. Well, if we're starting with x is our 1, this is a half and this is a half. So y is going to be 3 of those halves of x. Y is going to be 3 of those halves of x. On the other hand, when we want to use y as 1, then each one of those rectangles is going to be a third. Each one of these is going to be a third of y as well. So the x unit will be 2/3 of y. So make sure, take care to use your definition of multiplication to interpret the meaning of 3/3 and 3/2 and 2/3 suitably. Okay, so we are looking at 3/2 as 3 1/2. So 3 groups of 1/2. And we're looking at 2/3 as 2 groups of 1/3. And for those of you that took Math 112 with me, you would have seen this happen before, right? Where we interpret a fraction like 3/2 as a product of 3 and 1/2. 1/2 tells you what you are using, how big those fractions are, and the 3 tells you how many you have. Okay. Now let's look at how much information we can get from graphs and tables and equations of proportional relationships. So let's take a look. The table below shows total distance and elapsed time as Kelly, Devontae, and Heather walk along a running track. So we have a table for Devontae, a table for Kelly, and a table for Heather. So let's graph each of these students on graphs based on the information given to us in the table. So let's use red for Heather. And so we have the number of meters and the seconds. And meters are on the vertical, seconds are on the horizontal. So 1 meter in 2 seconds, 2 meters in 4 seconds, 4 meters in 6 seconds, 7 meters in 8 seconds, and 11 meters in 10 seconds, and then 16 meters in 12 seconds. And if we draw this, because we can measure their, and at 0 seconds, 0 meters, right? They start at the origin. If we draw this, we can measure their, Heather's time and distance at any given time, so we can draw a line through this. And let's try to look at Devontae. I'm going to move Devontae in green. So 3 minutes and 3 meters in 2 seconds, 6 meters in 4 seconds, 9 meters in 6 seconds, 12 meters in 8 seconds, 15 meters in 10 seconds, and 18 meters in 12 seconds. Now, when they start, they're starting together, so they'll start at 0, 0. And for Devonte, you'll notice that the distance that he is walking and the time that it's taking him actually has this consistency, right? So for every 2 seconds, he goes 3 meters. Okay, and let's try Kelly. And Kelly will make in purple. So Kelly is for 4 meters in 3 seconds and 8 meters in 6 seconds and 12 meters in 9 seconds and 16 meters in 12 seconds. Now Kelly is also starting at 0, 0, and she is also traveling consistently 4 meters every 3 seconds. So this is Kelly, and this is Devonte. So which students are walking at a constant speed, and how can you tell? I'd like you to look at the graphs and respond to this. So how can you tell that which students are walking at the constant speed? Who walked faster, Kelly or Devonte? Explain in several different ways how you can tell from their graph. Now, there are a few ways that